a problem anymore. So you can yell at your TAs for taking that question away from you. I'll try not to make it like way harder or anything, but we'll see. We'll see. I got to find something else to replace it. Okay, I think today's not going to be like too crazy. And it's like the lecture before reading week. Who wants to do more than we have to, right? I don't. I swear these pen, I don't know if it's the battery or what. It was doing so well. So well. So anyway, we're going to define improper integrals now. Instead of unbounded intervals, we're going to do unbounded functions. So, and these ones you have to be a little bit tricky because unlike unbounded intervals, you know when there's an infinity sign, right? Like if you take an integral and you see an infinity, you're like, oh, it's an improper integral. But for unbounded functions, it's not as clear, right? So let's talk now about unbounded functions. Right. Okay. So I do have a sort of like classic example of where this can go wrong. And in fact, if you're not paying attention, you can get bit by this pretty easily. So let's say you're asked to do something like what? So let's say consider the integral from like -1 to 1 over x squared dx. This is like the classic example that you can use. And again, if you don't recognize, so we know that this function is badly behaved at 0. But if you're not paying attention, you might just be like, oh, okay, well, I'll apply the fundamental theorem of calculus. And if you apply the fundamental theorem of calculus, you say an antiderivative for 1 over x squared is -1 over x. Evaluated from -1 to 1. And what is that? That's like -1 minus 1 equals -2, right? And this is, of course, is nonsense. Really, let's put that in big red letters. Okay, because I don't want you to see this and think that this is okay, right? This is bad. The first obvious indication, the function 1 over x squared is always positive, right? Yeah, so certainly, yeah, you're right. The function's not defined at 0. That's the reason why the FTC doesn't apply, right? The FTC doesn't apply because the function is not defined at 0, and therefore does not actually have an antiderivative on this interval, right? Or at least not a continuous antiderivative on this interval, which is what you need in order to apply the fundamental theorem of calculus. The other thing, I mean, there's a few other red flags here. 1 over x squared is always strictly positive, and yet somehow we integrated it and we got -2, right? Like that's clearly nonsense. That can't possibly be true. We can't integrate a positive function and get a negative area, right? So we have to just kind of be on the lookout for places where our function could be not defined. It won't be as clear in these cases where we have, if we have unbounded functions, right? Okay, so we can't do this. So the FTC does not apply. Since 1 over x squared is not bounded. So in particular, it's not even integrable, right? Since 1 over x squared is not bounded at 0, which is in this interval. Okay. So how do we deal with these functions? It's going to turn out this function is actually not integrable, even in the extended sense. But at least we're going to have an idea of how we can make sense of this. And basically, we're just going to do exactly what we did for improper integrals, but this time for unbounded functions. So we're going to say definition. So let's say, suppose f maps. Do I want to do this as an open interval? I don't think I do, but up to measure 0 and all that. Is unbounded at the point A, right? And again, what do we mean by that? I'm just going to say like the limit as we approach A from the left is equal to plus or minus infinity. Maybe let's put that in brackets. So the limit as x approaches A, or sorry, from the right is equal to either plus or minus infinity, okay? But is integrable on xb for all x n, for all x, in open interval AB, right? So it's not integrable, certainly on this interval, right? Because an integrable function has to be bounded, but it could be integrable just, slightly to the right of A. In AB like this, okay? So what we're going to define is the improper integral. So we define the improper integral. And again here, right, like you don't even see that it's improper, right? Like there's no obvious infinity showing up here, but you're keeping track of that hopefully. So the limit as x approaches A from the right of x bf, right? We'll say that the integral converges if this limit exists. So the integral converges if the limit exists. And diverges otherwise. Okay. And of course, this is, for the left endpoint, and we could do the exact same thing for the right endpoint. It really doesn't make a difference. So let me just maybe say that, similarly, if f is unbounded at the right endpoint, you can imagine what we're going to do. Right? And of course, then there is also a notion of two-sided, where if somehow you're unbounded at both endpoints, but you're integrable on any, closed and bounded interval contained within, between A and B, you can do it there as well. Now that's very rare. Almost never are you actually going to consider something which does that, but it is possible. It does come up from time to time. And the answer is the usual one, right? So if you're unbounded somehow, both of your endpoints, you're like this sort of, what function is that? Like arc sine sort of thing, right? You look like this big U and you have a vertical asymptote on either side. Just pick some point in the center, compute the improper integral to the left, compute the improper integral to the right. If they both exist, you add them up, you're done, right? Like that's how you're going to do it. The exact same way we would do it for unbounded intervals. Okay, so yeah, we can do it like that. And yeah, what's the moral of this story? I mean, yeah, we can just go straight to start proving convergence theorems. Because the reality is we're almost never going to do any of these in this class. They don't come up a lot in real life. It's nice to know they exist, but nobody cares. So I'm going to say theorem. All right, so there's another p-test. But now, this time we have to be careful because most of the theorems are almost verbatim copies of the theorems that we just did, where we were integrating from A to infinity. Most of those theorems are word for word verbatim, just with the appropriate things changed. The p-test actually does fundamentally change. It actually flips. So instead of p being greater than 1, being the convergence, it's now going to be p less than 1. All right, so it's going to be the integral from 0 to 1 over x to the p converges if and only if p is less than 1. Okay, this is notably quite different, right? When we were integrating from 1 to infinity, it converged precisely when p was greater than 1. Now it's going to converge when p is less than 1. And in fact, the only sort of interesting cases here are really p between 0 and 1, right? If p is negative, then this thing is like x squared or something, right? Or x cubed or the square root of x. And it certainly converges because it doesn't even have, it's not even an improper integral then. So the only place that this is really interesting is when p is strictly between 0 and 1. That's the sort of interesting thing that happens, right? Okay. And the proof is almost the same way, but this is kind of our example of having, doing a one of these improper integrals. So let's just give it a shot. But we're going to prove it in exactly the same way. We're just going to integrate, right? So the integral from 0 to 1. So that's going to be the limit. We need a new variable, c. Let's do c. Like that. All right. We actually integrated this last time. So, we can just write down the answer. 1 over, what is it? So it's negative p, but then you add 1. So it's going to be 1 minus p, 1 over x to the p minus 1 from c to 1. So that is the limit c goes to 0 from the right, 1 over 1 minus p. And again, right, p is not equal to 1 because if p is equal to 1, the usual issue. It's, in this case, it's less than. Yeah, we really do mean less than. And this is the point, right? Like the last one was greater than, and this one's actually less than. And we'll see it in a second, right? We'll see why this is true. Okay, so if I plug in 1 into this, what am I going to get? I'm going to get 1 minus 1 over c to the p minus 1, like that. Okay, now for this limit to converge, because this isn't an integral or anything crazy, for this limit to converge, like everything here is well defined for the most part. The only thing that we run into trouble with is if this exponent is actually positive, we're in trouble, right? We actually need this exponent to be negative. So we need this to be negative, right? Because if I have anything that looks like 1 over c, or 1 over the square root of c, or 1 over c squared, or anything like that, I'm in trouble. It's not going to work out. I legitimately need this thing to end up being, 1 minus the square root of c or something, so that the limit exists. Okay, so I can't have this be 1 over c. It's really got to be c to some power. That means that power has to be negative. So this converges precisely if p minus 1 is less than 0. And this converges if and only if p minus 1 is less than 0, i.e. p is less than 1. Okay, and again, you check log, but it's obviously, this is the p does not equal 1 case. And then the p equals 1 case is just, again, it's log. Log does not exist, right? The issue is going to be you're taking the limit of log as you go to 0. That obviously doesn't exist either, right? Here, let's just do that in quickly. If p equals 1, the integral from 0 to 1, 1 over x dx is the limit as c approaches 0 from the right of 0 minus log c, which clearly does not converge. Right? And so just like last time too, this is an if and only if. Okay, yeah, so I mean, this one might help to do it like with an actual number. So let's just kind of the only thing we're interested in here is this thing right here, right? Everything else is actually sort of constant in C, right? This is the only thing that matters. So what we could do is we could actually look at, let's think about, I think it'll actually, it's not even that it disappears fast enough. Here, the only way this limit makes sense is if this isn't actually 1 over C, right? So here, let's try a couple of values. Let me show you what I mean. So for example, if P is equal to 1/2, right? And maybe let's just write this as a case. And then if P is equal to 2. So let's compare these. So if I do the integral from 0 to 1 of 1 over the square root of x dx, right? That becomes the limit as c approaches 0 from the right of what? So root 2 1 over 1 minus p, so this is 2 times 1 minus 2 root c. Right? Does that make sense? So that's basically me, like if I just go up here to this equation right here, and I plug in p is equal to a half here, this is what I get. And this definitely converges because the square root of c, right, as c approaches 0 from the right, yeah, that totally exists. So this is just going to be equal to 2. Okay, but if I do p is equal to 2, that's going to be the limit as c approaches 0 from the right of what? So we're going to get 1 over c minus 1. And that doesn't exist because I've got this 1 over c term. Right? So basically, unless your exponent is negative, right? That's why we need this exponent to be negative. Because if that exponent isn't negative, it really is 1 over c to some positive power. That thing's not going to converge because we know that 1 over c to any power is going to give you trouble as c goes to 0. So what we need very specifically is that when I integrate it, right? Again, we kind of know that the antiderivative of 1 over root x dx is what? It's 2 root x or whatever, right? So notice that it's not 1 over anything anymore, right? Or if I do the integral of like 1 over x to the 1/4 dx, right? Okay, somebody double check me here. So this is what, 4/3 x to the 3/4? Pretty sure, right? And again, it's not 1 over x. Maybe let me throw my plus c's in here. But if I do something like the integral of 1 over x to the power of 4, that's what, -5 over x to the 5 plus c, and I get this 1 over something. Does that make sense? Is everyone seeing what the issue is? I need to, when I actually evaluate the antiderivative, it can't be 1 over x to any power. I need to make sure that when I anti-differentiate, I actually just get, even if I write this as maybe x to the half, I don't have 1 over x's appearing anywhere because I'm taking a limit as I approach 0. Right? And if you ask yourselves, what sort of powers do I have to start with to ensure that when I add 1 to everything, I don't get a 1 over x term? The answer is, well, the power that you started with had to be less than 1 itself. So does that make sense? Does everyone see what needs to happen there? Like why that works out? Is that okay? Now, there is a sense too in which, like, yeah, what are we trying to say? Like when we write this down, we're trying to say that basically the function explodes. What do I want to say here? Does it explode quickly? Yeah. The function sort of explodes slowly enough that it converges. Does that make sense? Like that's, so with 1 over x squared, right, when we were doing the p-test from like 1 to infinity, we needed that the function went to 0 really, really quickly, right? And that was our sort of intuition for why this worked. 1 over x was like sort of this limiting case. It went to 0 really, really slowly and just really slow enough that you would actually get this infinite integral out. But 1 over x squared really drops off, and it drops off fast enough that your limit actually, your improper integral exists. It converges. 1 over x cubed, 1 over x to the 4, all those things as well. They go to zeros really, really quickly. What you need for the improper integral to exist is that it explodes slowly, right? If the function if the function shoots off to infinity really, really quickly, then you're going to add a lot of area underneath the graph when you take this limit. So you need that it explodes slowly, right? It goes slow enough off to infinity that you actually only accumulate finite amount of area. So hopefully that makes sense, right? You need slow growth when you're shooting off to infinity and fast growth in the other direction. And believe it or not, there are functions too where say they're unbounded functions and you can integrate them on unbounded intervals, and both of those exist, right? So you have both types of improper integrals. Let's say you integrate from 0 to infinity and it's unbounded at 0 as well. It's possible these functions do exist and you can actually do both sorts of improper integrals on them, and it totally makes sense and it's cool. Okay, so actually fun exercise, see if you can find one, which is, I think, is a nice thing. And then without going into much detail, because again, we're not going to do this, I think this is actually probably a really good exercise for you to try and do, is basically theorem, or let's say exercise. These proofs are a little bit weird, again, because nobody does these, but one, state and prove the basic comparison test for these improper integrals. Okay. And the statement is exactly the same sort of thing, right? You've got two functions, maybe they're unbounded at 0. One of the functions is always bigger than the other. If the smaller function diverges, the bigger function diverges as well. If the bigger function converges, the smaller function converges as well, right? It's the exact same statement. And the proof itself is almost identical as well. You just kind of have to manipulate, right? If you look at the proof that we did on Tuesday and you do the appropriate manipulations, where now you're taking a finite limit instead of an infinite limit, it's the exact same proof, okay? It's pretty much identical. So that's number one. Number two, you can probably guess, state and prove the limit comparison theorem. Again, exactly the same statement. For these improper integrals. And three, is there some notion of absolute convergence? I don't think there is. So I guess maybe we should ask ourselves the following question. Is there a notion of absolute convergence? I suppose you could make one up. But yeah, I guess if like your limit didn't exist because it oscillated, it oscillated infinitely quickly, and then the amplitude of its oscillations became very big, but that probably just isn't going to exist in the first place. Oh, could you make it exist? Oh, that would be dirty. That'd be an interesting example. Maybe that, no, I've already asked too many improper integral questions. Yeah, I feel like there isn't a good analog of absolute convergence in this case, but this would be an interesting thing for someone to play around. Okay, yeah, I mean, if the textbook says yes, I mean, we can't, I mean, past me was much smarter than current me. So if we trust past me, then that's good. Did I ever tell you guys the story? So I was, what year was I in? Might have actually been my like first year, 671. Oh, nice, I'm there. Okay, look at that. I guess there is one. Oh yeah, and I give it even examples. So I was in grad school and I was taking like, doing graduate algebra, which is just a repeat of undergraduate algebra, but, slightly more on drugs. And I'm stuck on this question. So I go online to look it up and to see if I can find, if anyone has any clever ideas about how to do it. And I find this post on like the physics forums, right? And I'm like, oh, okay, like this person had an idea here. It seems very insightful. Like that's really, really clever. And then I look at the poster and I realized it was me from like 3 years ago, was the person who was answering. And I was like, oh man, I was way smarter back then than I am now, apparently. So this has legitimately happened to me, like actually multiple times. I think probably 3 times in my life now, where I've looked something up and I've realized that I have answered it, like, old me, previous me has figured it out and actually has answered it. And then I forgot and then had to look it up again. So this is totally a thing that can happen. So yeah, that's why when I say past me was so much smarter. But okay, but like, have none of you ever looked back? Even something that I get nowadays is like, if I go back and I read even my writing, like my some of the stuff that I wrote in like high school, I was a much better writer in high school than I am now, right? Like my writing has just gone to crap because I write like a mathematician now, right? Like I start sentences with the word then, and all of my fancy language is just technical math words, right? It's not like I was actually much better at prose as a high school student than I think I am now. So yeah, it's one of these weird things where you had a skill and then you lose it and you look back and you're like, oh man, I was clearly much better back then, right? Same thing, like it would take me a couple of months to get back into my research game, right? Like really cutting edge. And if you don't do it, you lose it really, really quickly. Yeah. I mean, well, because what it is it's like you're an athlete, right? When you take a test or something, you're usually at your apex, right? Like, well, I mean, right. So you studied, you've been practicing, you go into that test and you're as ready as you'll ever be. And then if you look back on that, some indeterminate period of time later, whether it's weeks or months or years later, you haven't been doing it. You're not at your prime to write that test like you were when you wrote that test, right? So obviously you're going to look back at that and you're not going to be as strong as you were. So I think that like that's not even necessarily a weird thing, right? It is weird finding an internet post, like a forum post of yourself years later, but yeah, I think this isn't actually too crazy. Okay. And then, yeah, I guess, is there anything else? I don't want to talk about improper integrals anymore. I hate these ones. These improper integrals suck. The other improper integrals are great, and we will use the other improper integrals. These improper integrals suck. I'm trying to think if there's anything in my life where these have actually come up. And I want to say no. I can't think of a single time in my life where I think these sorts of improper integrals come up. Like I said, these are okay exercises for all of you. I think that getting, first of all, some practice trying to figure out what the statements should say is a good exercise. And then adapting the proofs that we did on Tuesday to prove these sorts of things is a good exercise as well. So I think that these are good exercises for you, and to come up with examples on your own to see if you can do it. Is measure at least is some, I don't know what to tell you. These integrals are just boring. Like measure is interesting, but nasty. Like that's the sort of thing. These aren't hard, they're just lame, right? Like lame is somehow the best word that I would have to come up with them. So I don't want to do it's like, there are a bunch of first year things that I think are lame and don't want to do. So I don't know if any of you did like curve sketching in high school. I think curve sketching super sucks. And if I ever teach calculus, I don't teach curve sketching. Right? Because I refuse to do it. Like it's super. So, okay, it depends on what you mean by volume though, because volume can be cool. I think volume can be cool if it's taught correctly. Like volumes of solids of revolution, like those things. Like, yeah, no, that stuff could be fun though, right? So I think the way it's taught in high school is terrible, but the way, if you do it correctly, it can be a lot of fun, right? So the way a solid of revolution comes, basically, because yeah, I'm not doing any more improper integrals. We're done about that. No. I'll talk about it if you come take. Do you know? Okay, maybe I will. I'll explain it kind of briefly. But anyway, here. So you take, for a solid of revolution, right? Suppose that you have some sort of shape and you rotate it about the x-axis, right? You do something like this. Let's say you get this thing. And I'm going to try and draw the picture like this, right? So this is your solid of revolution, and you're going to do shells or washers or whatever it is. Now, so the cool thing is, if you learn this from sort of the typical high school way, it's dumb because they're just like, here are a bunch of different formulas that you should memorize, right? If your function is this and you're rotating about this axis, you use this formula. And if you rotate about this axis, you use this formula. So when I used to teach this, for example, I used to teach 132 and 134. I actually used to run that course for a bit. It was interesting because the students had done this in high school and they hated it there too, but we taught it in a slightly different way. And then they really, really liked it. And so we didn't teach any formulas. Okay, we taught zero formulas whatsoever about doing solids of revolution. And we said, listen, just think about the problem, right? Here's your function. It's like, I don't know. Well, let's just keep it abstract. We'll call it y equals f of x. And what I want you to do is take a cross-sectional cut, right? So just, here's a point. Let's call that point x. And then all I want you to do is just cut your figure there and look at the shape that it makes, right? So it makes this sort of like circular thing. Okay, what is the area of that circle? Well, if you kind of zoomed this circle up, so now let's pretend I'm kind of like staring at it down the y-axis, right? Like the y-axis is pointing at my face. It's a circle that looks like this. And its radius is exactly just whatever f of x is, right? So the area of this circle is pi f of x squared. And then if you integrate all of these areas, you get the volume, right? So let's say this point here, the first point is A, the end point is B. So you get volume is the integral from A to B pi f of x squared dx, right? And there you go. There's your formula. If you rotate about a different axis, you just do exactly the same sort of thing, right? So you rotate about a slightly different axis, your circle is going to change, but that's it. You just still take a cross-sectional area, figure out what the area of that thing is in terms of f of x, and you integrate, and you're done, and you're fun. Now, those of you who have learned, you've probably learned this is the, I think this is the washer method. And then there's also the shell method, right? So the shell method is where you like make a cake. And I don't want to go too much into this, but you know, in no time there's never been a calculus class that I've seen that has ever proven why those two things give you the same answer, right? In fact, proving that whatever this thing is actually the volume is usually something we skip. Like, how do we know this actually gives you the volume? You know what I mean? Like, we've done it, we've determined the cross-sectional area, we've integrated the cross-sectional area. Why do I actually know that the cross-sectional area is the volume? There's a proof for that. You actually have to prove that. You have to prove that it works. So that's number one. Number two, if I integrate using shells instead of washers, why do they give you the same answer, right? And there's a proof of that. And that proof is insane. That proof is one of the coolest things I've ever seen in terms of integral calculus. And the answer is this very old theorem. I feel I've mentioned Pappus's theorem in one class. Was it this class? I don't remember which class I mentioned Pappus's theorem in. Did I mention Pappus's theorem in this class? No. So do you know what a geometric centroid is? Pappus, P-A-P-P-U-S. Okay. Does anyone know what a geometric centroid is? Okay. So Sophie, you just know my book better than I do, which is crazy. Sure, yeah, the centroid of a triangle is a type of centroid. And yeah, okay, so 627 exactly is the theorem that I'm talking about. Yeah. So, so the geometric centroid is the center of mass. You can think about it like that, right? So for those of you who are maybe more physicsy people, the geometric centroid is the center of mass. It's basically, if I give you a shape, right? I think the geometric centroid is probably going to be about there. So if you cut that you cut that shape out on a piece of paper and then balanced it on the geometric centroid, it would actually be balanced, like it wouldn't fall off, right? So the geometric centroid is the center of mass. Then you have Pappus's theorem, which says if you take a shape like this and you rotate it about an axis like this, right? Then the volume that it sweeps out is proportional to how far the geometric centroid traveled. Okay, so this is Pappus's theorem, is you look at how far the geometric centroid traveled, and you basically multiply that by the area of your shape, and that is the volume that you create, which is, again, even just physically an interesting thing. It says that in some sense, you can approximate your volume just by looking at a point mass, right? We do this all the time in physics where we say, you know, if I'm standing on the surface of the Earth, it's like I'm experiencing the Earth's gravity at a distance, like if all of the Earth's gravity was packed into a single point at the center of the Earth's core, I'm experiencing that sort of thing. So, you know, it's very similar like that. Now, it turns out if you compute the geometric centroid, right, if I give you an arbitrary shape and you compute its geometric centroid, and then you rotate that geometric centroid around, you get, like, basically the X and Y coordinates of the geometric centroid are precisely, one of is the the shell method, and one of them is the washer method. And so, like, this is crazy, the fact that this works out. And again, no one ever talks about it, which is, you know, a real shame. But it's such a cool thing. So yes, if you have my book, I do talk about this. As Sophia's pointed out, this is section 7.5 and 627, precisely the exact page number. But 627 is exactly where to find it. So if you want to read about it there, you can. But yeah, I actually don't hate volumes of revolution. I agree with you, Sophia. I think they suck the way they're traditionally taught, but I think that there is a way of teaching them that that doesn't suck. So sometimes it's just about how you teach them. That being said, there's almost no way to teach curve sketching that doesn't suck. There is one little thing you can do where you add a parameter to your curve instead. So it's like if I made you do, instead of saying like plot x over 1 minus x squared, right? Something like this. It would be something like, I don't know, x to the alpha, over 1 minus x squared. I said determine the different, like qualitatively, if you change alpha, how does that change the graph? So something like that is actually okay as a curve sketching exercise, but still curve sketching sucks. So I don't want to curve sketch. I'm never going to curve sketch if I don't have to. So yeah, anyway, basically, moral of this story is I'm not going to talk about improper integrals anymore. I'm going to leave that for you. Very quickly, since we're basically just in bonus time now, what is dx? So dx is very hard to describe. It has many different interpretations depending on what you're doing. So if you study more measure theory, dx is actually the measure, right? So it's actually the thing which is determining how wide your measures are. So in fact, what you'll sometimes see people do is instead of writing, the integral of x dx, they'll write the integral of x d mu, where that's like the Jordan measure or something like that. Okay, so there's some instances in which this is the interpretation of the dx is as a measure. Sometimes it's as a differential form. What is a differential form? Way too complicated to explain. So the one that might be accessible to you, are you all in linear algebra and or have taken it already? I think that's probably true, right? Like everyone's probably at least in 240 or have taken 223. Okay, so if I give you, this might be beyond your knowledge yet, but if I give you a map, let's just do Rn for now. So let's say I give you a linear transformation from Rn to Rn. Okay, and you might not have learned about linear transformations yet, but they're basically just maps of vector spaces, right? If I give you a linear transformation from Rn to Rn, there's this special thing that you can compute about it called the determinant. Okay, so have people seen this before, like what the determinant is? Okay, what is the determinant? Can anyone tell me? Okay, sure, yeah, it's the area. It's the area of what? It does give you the area of a parallelogram, that's true. Sure, yeah, that's maybe a better interpretation. The determinant accommodates and tells you exactly how the area of a parallelogram changes, right? Or more precisely, parallelogram is R2. In Rn, it would be a parallelepiped, right? So given a parallelepiped in Rn, so if P, yeah, we kind of talked about this when we did measure, didn't we? So if P in Rn is a parallelepiped, and I'm going to misspell this because of course I will, parallelepiped, then basically the measure of TP, i.e. its volume, is the determinant of T times the measure of P, right? So the determinant tells you precisely how the volume of the parallelepiped is changing. Now the problem here, and yeah, so this is kind of related to change of basis. So the problem is that when you have a change of basis, right, when you change the basis that you're working in, how do I want to say this? So first of all, changes of bases are very restrictive because they all, first of all, effectively have to be rectilinear, right? Like for example, have you guys learned about polar coordinates at some point in your life? Probably, right? Like x, y equals r cos theta, r sine theta. Probably learned about polar coordinates, right? So instead of thinking of points in terms of their x and y coordinates, right? How far you are along the x direction and the y direction, right? Instead, what you do is you think about them as basically where they lie on a circle of radius r, right? So you can write things in terms of r and theta instead, and r describes how far you are radially away from the origin, and theta describes at what angle you have to travel away radially from the origin. And you can see every point that isn't the origin can be uniquely described by an r and a theta, right? Just like every point in the plane can also be described by x and y. Now, the problem is that this is not a rectilinear change of variables, right? Effectively, if you change a basis, so if you're looking at points in R2, so again, here's my point in R2 now, and let's say I have a basis, right? One basis is the standard basis. And if you write x, y in this coordinate basis, you get some representation, right? But you could change the basis, and you could use this basis instead, and now the representation of the point x, y changes. But at the end of the day, these are all rectilinear bases, right? Like these bases are effectively just, they look like, if you were to plot the 1, 1, negative 1, 1, what do they look like? Like if you draw the grid, which corresponds to this second basis, it looks like this, right? Like that's the grid of, that's the integer lattice for this basis, right? Yeah, exactly. Or they're parallel. Maybe that's a better way of thinking about it, is the lines, they're straight lines, and the straight lines are always parallel to each other. And they might not pass, right? Though again, remember with bases, so in this case, I chose two bases that actually do hit at 90 degrees, even if I haven't drawn them that way. But of course, when you're dealing with a basis, you don't need that requirement, right? Your bases don't have to be orthogonal. But nonetheless, when you draw their grid lines are always parallel. If you draw the grid for polar coordinates, right, it looks like this. Right, something like that. Right? So you just take integer values of your radius, you take integer values of your theta, and of course you get something like this, right? Like the integer values would be, for theta, might be more packed. But this is a problem, right? Because now what I want to do is I want to figure out how areas are changing. So let's zoom in on something. So let's zoom in on this. Here, maybe let me redraw this. So if I choose something like this thing here, so let's see, maybe that looks something like, right? That's the area of that little shell. So as kind of pointed out, we have, I can figure out exactly in the red thing above, I know exactly what the areas of these squares are, right? Because that's the determinant of the change of basis matrix between them, right? These are parallelograms or parallelepipeds. This new grid relative to my old grid, I can figure out exactly how the areas of those things have changed because I can just compute the determinant of the change of basis matrix, right? The problem is that I can't do that here, right? The determinant is not going to be able to give me anything because first of all, I just don't even have I don't even have a matrix. And even if I think of this thing as a map from R2 to R2, it's definitely not linear, right? So the question now becomes is how can I figure out if I start with something which looks like, kind of our boring normal integer lattice, and I map this rectangle onto this rectangle, how can I compute how that area changes? And you'll notice that this is also so much worse because the areas change depending on where you are. In the red picture in the top right-hand corner, all those parallelograms are the same area, right? If I draw the integer lattice, all those parallelograms have the same area. But for polar coordinates, it depends on how far away you are, right? It depends on how far you are radially, right? Because if I take this rectangle, it's definitely a different size, right? So this is what dx is effectively doing. Dx is figuring out if you have a nonlinear change of variables, how is the scale changing, So when you do something like you write, so yeah, there's a sense in which the dx is, dx, when you write dx and you're just kind of being boring and you're saying like, yeah, x is just the measure. I'm applying the identity transformation. I'm not doing anything. So again, that's why it's the measure, right? The dx term is saying, I'm just looking at the function f of x equals x. This is my identity transformation. How do volumes change under this map? Well, the answer is they don't, right? This map doesn't do anything to the real line. It just takes every interval, maps it back to itself. So the area is not changing. But when you do something like substitution, and you say like u be x squared, du is 2x dx, now du means something else. Now du is saying, listen, in the u world, you've changed your variables. Now everything is in terms of u, but you couldn't do that for free, because when you did that, you were actually changing how the lengths are scaling. And when you change how lengths scale, when you integrate, you need to keep track of how you changed your Riemann sums. Like basically, you started with a rectangle. Once you change variables, that rectangle might expand or might squish. And depending on how far along the x-axis you are, you're going to get different amounts of expansion and contraction. And that's what this 2x dx term is doing. It's keeping track of the rate of expansion of that interval after you've made that substitution, so that when you do the integral, when you actually compute it, you still get a number that is valid. Does that kind of make sense? It's a little bit tricky to see. This will actually become, believe it or not, this will become much more clear in multiple dimensions. But that is effectively what's happening here. It's tracking your scaling difference. And so while du is now, kind of boring and simple in the u world, if you're in the x world, your scaling was doing something different. So again, if you take second year calc, this should become actually a little bit more clear. But that's effectively what du and dx are doing. Yeah, exactly. I mean, they could, they don't have to, but right. But like, look at this. If I say u is equal to x squared, right, then what I'm effectively saying is like, what's the difference between the number 0 and 1 under this map, right? If x equals 0 and x equals 1, how much does u change? Well, u only changes by 1 as well, right? But now when x is equal to 2, u is equal to 4. The distance here has actually increased, right? So the scaling distance, by defining u to be this new variable, the distances are actually stretching as x becomes bigger, right? The distances are stretching out. And so to keep track of that in the integral, right, we need to track that. That's what this 2x term is doing. It's keeping track of how much the scales are changing, right? But at an infinitesimal level, right? This is the other important thing to do, because you might say, well, like, wait, how is 2x coming into this? This jump here is 1. This jump is 3. Like, it's not doubling in length. That doesn't seem to be what's happening, right? Because it's actually more complicated than that. It's 2x at each point x, right? This is an infinitesimal scaling. When x is equal to 1, we're infinitesimally scaling by 2. When x is equal to 1.1, we're infinitesimally scaling by 2.2. When x is equal to 1.2, we're infinitesimally scaling by 2.4, or whatever it is, right? And then when we integrate that infinitesimal scaling, we get the total scaling on that interval, right? So that's what we're doing, is we're computing that scaling infinitesimally at every single point. We're integrating that scaling, and it will give us the overall global scale factor. That is effectively what's happening there. This is hard to see, though. Again, it's weird because this is hard to see in one dimension. Ironically, it becomes much easier to see in 2 dimensions. That's why I was kind of talking about this polar picture, because I think you can see that, first of all, again, in this polar picture, as the radius gets bigger, your rectangles are actually getting bigger as well, right? So it actually seems to suggest that, your rectangles are changing in size infinitesimally, but they're changing in size, and they seem to be getting bigger as r goes off to infinity. And if you compute what the corresponding d x dy is in terms of dr and d theta? The answer you get is r. And that's exactly right. It's saying as r gets bigger, your rectangles get bigger. And so that's exactly what's happening. So that's that scaling factor at work again. Okay, so anyway, I don't, none of this is rigorous right now. I don't really want you to worry about it too much. This is just an idea of what's going on. Yeah, I mean, like, again, this is, if you're kind of interested in diving more into this, you can look up something like change of variables. Some people actually call it substitution change of variables instead. There is some trickiness here, which is really annoying, which is when we talk about change of variables in multivariate calculus, we often don't have oriented integrals. And when we talk about it in first year calculus, we do have oriented integrals, right? In the sense that a to b is equal to, not a good time for the pen to die. But if I switch those bounds around, right, I get the minus sign, right? So if I integrate from b to a, I get negative. And you don't have that in multiple dimensions, because what does it mean to switch the bounds around, right? You're integrating over sets, not just intervals anymore. So we have this in one dimension. And substitution changes because you don't have a corresponding analog of that in multiple dimensions, which means an absolute value shows up instead. So you actually could restate substitution in terms of an absolute value. Yeah, maybe let's not write it as an oriented integral, so it's not obvious what I mean. G of A, G of B. I should just say whatever the image is of AB. Right? This is sort of like how you would do this if you didn't have the ability to switch your bounds. This is how you would write substitution. And then the absolute value might scare you, but again, it's just accounting for whether you're negative or not. The other thing that happens with change of variables is you're only interested usually in diffeomorphisms, whereas we were definitely allowed to use non-diffeomorphisms in our case, but then there's an argument, if you only use functions of bounded variations, then those functions are always piecewise diffeomorphisms, blah, 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 whatever. It's some high level analysis stuff, right? So anyway, there's some interesting stuff here. I'd say, it's probably actually not even worth worrying about until a little bit later. Wait until second year, and we'll cover this in like a lot of detail. But yeah, if this is interesting to you, check out change of variables. That's where this thing goes into much more detail. Yeah, my 237 notes are up. You can definitely take a look at those as well. And I do talk about change of variables a little bit there. So you can try that. But yeah, that's going to finish it for today. And I'm very thankful I didn't have to talk about improper integrals more than I had to. And then, yeah, other than that, everyone, next week is reading week. So of course, it means there's no office hours on Monday. I'll still check out Piazza on occasion, but no promises. No lectures, no tutorials, no nothing. Use the following week to try and just catch up on your stuff, recharge your batteries. When we come back the week following, there will be a term test. So tomorrow I will post term test information, even though the term test isn't for 2 weeks, but it's the next academic week, right? So just I'll post that information tomorrow. But otherwise, just relax. You don't have anything that you have to do, right? Like you submit your assignment Friday night and you're done. I do that on purpose. I don't want you to have anything to worry about in reading week. Just try and relax a bit. And then that way, when you come back at the end of February, you're good to go. Okay? Any last minute questions? No problem. Thank you. Yeah, have a good weekend, good reading week, everyone. No problem. I will try. Okay, everyone. I'll see you next week. Not next week, 2 weeks. See you in 2 weeks.